and 14 is the date. So September 14, 2015, our detectors were just up after a 5-year break for making big upgrades and engineering improvements. And we saw a signal that was almost too good to be true. And then since then, we've seen a number of other signals too, but that was the original one, the one that caused all the excitement and fuss. So what did we see? We saw these two black holes, and they were orbiting each other, and they collided. That's what black holes do. And then this gravitational wave propagated out into the universe, and it traveled across the universe, and it traveled, and it traveled, and it traveled because it went a very long ways. It traveled for a long, long time. We know now it traveled for 1 billion years. And then it came to our beautiful little Earth, arriving first at our Louisiana detector, and then just a short bit later at the Washington detector. Here's the wave coming through, and it shook our Earth, but not like this. This is clearly very exaggerated. It shook our detectors, as I told you, by less than 1,000th of a proton. Okay, but the detectors were up and running. They were working, and they saw this. Now, remember that movie I showed you, or the bumps and wiggles that Kip Thorne had predicted? This is the data that came from those beautiful, very clean-looking computer simulations. This is what happens when you have a real instrument. But these bumps and wiggles contain all the information about these two black holes. But I'll start by telling you two things. This is the amplitude of the wave. This is time. So you can see from this that this is 0.2 seconds. It's very short. These black holes orbited each other for over 1 billion years, and we saw the last less than a second of their lives before they crashed. Okay? Look at the scale. When they touched, the amplitude of the wave was that terrible number I told you, 10 to the minus 21, which is an enormous check mark for Kip Thorne. He told us in 1967 that this is what you'll need to look for. Okay, so check for Kip. The amount by which the mirrors of our detector moved was a few times 10 to the minus 18 meters, which is what Ray Weiss said you need to do. Check mark for Ray. Okay? So these guys got it right 40 years ago. And what we learned was that these two black holes, weighed 30 times the mass of our sun. So our sun we always think of as the biggest, heaviest thing we could possibly imagine. These things were 30 times heavier. They were traveling at almost at half the speed of light when they crashed. So imagine that you could accelerate something that's as heavy as our sun to nearly the speed of light. In no one's imagination is that possible except nature's. Nature does these things, and we can only be awestruck that you can do that. If we try to accelerate something, we cannot even accelerate an electron, a teeny tiny light electron, to nearly the speed of light, and yet nature does this with something this big. We know that these black holes were 1 billion light years away, and the most remarkable thing was that when the two black holes collided, they form a new black hole, and the new black hole was lighter than the two parents, which means 3 times the mass of the sun was radiated away as energy in those 200 milliseconds, which means it's the most powerful explosion we've ever observed. Okay? So these are the things that excite and make this very cool. I'll skip this. Then, 2 years later, again, now this is the year 2017. This you may not have heard about, or maybe you did. August 17, 2017, LIGO, and this time with our partner Observatory Virgo, the Italian detector, saw for the first time collisions of neutron stars. Now, neutron stars are cousins of black holes. Now, how are they related? They're related just by the fact that neutron stars are light. If a star were heavier, it would form a black hole. So they're like just lighter cousins, but there's one really big difference. What do you think neutron stars are made of? Neutrons. Exactly. Neutrons are the building blocks of all atoms. And so when you have a neutron star collision, you are building new atoms. Okay? And that was something that we've never seen before. So let me show you what happened. Now let me give you another thought to contemplate. If I took 2 billiard balls and I crash them together, just at normal speed, just throw them together, will you see any light come out of them? If it's in a dark room? No. You'll hear a sound, you'll hear them crash, but no light. if you were able to accelerate those billiard balls to extremely high energies and then crash them, you would see a flash of light because all the atoms of the billiard ball got heated up with all that energy. And that's what these neutron stars do. So I'm going to show you a movie of what they do. They've collided. The first thing you see is they're orbiting each other. You see the gravitational waves. But in the moment that they collide, and for a while after that, you see this incredible, spectacular light show. All colors of light comes pouring out. And so this detection that LIGO made was followed by this incredible Technicolor light show that was observed by more than 70 telescopes in the world. It's now already become the most observed object ever seen by astronomers. But let me tell you the story. It's a really fun story as well. So this is a detailed thing, but what it really shows is here is what the gravitational wave signal saw. And we know these are neutron stars and not black holes because the signal lasted over a minute. So neutron stars are lighter. And then there was a telescope out in the sky. It's actually a space telescope called Fermi that looks at very energetic light, gamma rays. And 2 seconds later, they saw a big spike. So here's the process. We saw the neutron stars going around each other, and right there where our signal ends, they collided. And a short 2 seconds later, there was this explosion of light. And so this happened when, let's get this part. This happened when it was, let me show you this. This is actually fun. So you can tell where this happened. It happened in this part of the sky, which happens to be in the southern hemisphere. And when it happened, when we saw the signal, it was daytime in the southern hemisphere. So astronomers had 12 hours to get their telescopes ready by the time night would come to point to where we said this had happened. And so in those 12 hours, they got ready. And then it became like an incredible night to remember because 70 telescopes all over the southern hemisphere pointed at it, and they saw all colors of light. Every color of light came out of this object at different times. So this is a very busy plot. I want to show you just a few fun things about it. The first thing is, these are just the names of telescopes, and these are how many hours later. So 10 hours later, 11 hours later. And all these different telescopes are slightly different colors. So notice something important. So these are optical telescopes. These are photons our eyes can see. In the X-rays, it came 9 days later. In the radio waves, it came 16 days later. So all these different colors of light start coming at different times. And that tells us about everything that was going on inside this collision. So let me show you what it does tell us. And how do we know this was the right object that they found? Look at this. 20 days before this telescope imaged the same galaxy, and there was nothing there. And then it showed up here. So we know this was a new light source that was formed. And so here's the movie now. 2 neutron stars going around each other. These are the gravitational waves. Then they collide, you'll see, and all this material comes out in this incredible collision. There. Jets of matter going out, neutrons spewing out of there. And the dramatic music was our own addition, of course. Yeah.
Maybe it's the gravitational waves.
What's that?
Maybe it's the gravitational.
It's maybe the gravitational wave.
But then no chirp.
Yeah, no, the chirp was there. I just, the music did play. That's right. So what you saw in this explosion in this movie that we see was a great deal of detail, and what ended up happening is we solved some decades-long mystery. So let me tell you. So this is a fun plot. Look at the days going by. This is simply showing the different colors of light. Each of these bumps is showing a different color of light that became more or less visible as the days went by. And by looking at these bumps, we can tell what kinds of atoms were being produced. And you'll have to take my word for it because I'm not going to go into any details, but this process, these bumps that we saw being produced are the production of heavy elements like gold. Okay, gold was being made. This is now called nature's gold mine. So let me tell you what was so funny about these decades-long mysteries. So I'll only talk about this middle one. So for a long time, we have not known where gold comes from. We know that we're made of elements. We know all the elements of the periodic table are formed in stars. That's where our stuff. The Earth doesn't make gold. We just mine it. It's already there from the formation of the Earth. But we know that stars don't make as much gold as we see. So we didn't know our gold, platinum, all the heavy elements, plutonium. We just didn't know the stars don't have enough neutrons to make these really heavy elements. So we've not known where gold comes from, and astronomers have scratched their heads for a long time. And that picture that I showed you of the production of gold now matches up with what we see, which is that gold and platinum are formed in these collisions of neutron stars. So that's one example of many mysteries that we haven't known about that was solved by these observations. So if you don't remember anything else about my talk, you should remember we found nature's gold mine. All right, so I'm just going to end by telling you that this is so what were the Nobel Prizes for? Really, there's a number of things. These were the first direct observations of gravity, so his theory is confirmed. These are also the first time we've seen neutron stars and black holes collide. We've not even known if they could do that. The fact that they do is comforting. And then my own role in this has been, for all of the time that I have worked on this, I have been part of building the instrument. I have trained with Weiss, and I've built different pieces of the instrument. So I have to say I'm really happy that the damn machine worked as well. Okay, that was a big relief. So these are nice, and these are the things we celebrate today. But really what we've done is something much, much bigger, which is we've sort of invented a new way to look at the universe. We no longer need to look at just light. That's what we've done for millennia. Humans have looked out into the sky with their eyes for millennia and wondered what's out there. Now we're actually saying you don't have to use just light. You can use gravity, and that's really important because we know there are many things that are dark that don't give off light, but they give off gravity. Okay, so that's really So I'll give you a little thought to end with. Let me just say this is for the kids and the young women in the room. I want to say something important here. So you see these guys, and I have these three guys. You can tell they're all really old, and you can tell they're all really men. And I've told you why they were important and how important it was for them to get this Nobel Prize. But I want you to see that there are younger people and there are women who are involved in this work. So here we are in Stockholm, and you can see a number of women in the crowd of us all gathered for the Nobel ceremony. So many, many younger people are involved in this enterprise now, and also, so you don't just have to be a very old man to do important scientific work, okay? So remember that, kids. All right, a bit about my own story, since people like to know. So this is my life in science. Here I am in the 1990s as a graduate student. There's Ray Weiss, and this was our group at the time. And remarkably, many of these people were in that picture I showed you in Stockholm from just a few weeks ago as well. This is our group many years later. So this was in 1993. This picture was taken in 2015. And in the meantime, I went from being a graduate student to being a professor in this group. Here is me working in my lab. This is what I do. And then here is me doing the gravitational-wave dance with Neil deGrasse Tyson. I put this out there just to show that a life in science can be very fun and exciting. You can also have some adventure. So here is a picture. Here I am again. This was in 2001. We were at the Washington Observatory watching a terrible desert fire coming towards our observatory. It was a wildfire. And it turns out that the observatory, the long tunnel that we have, broke the fire path to the town to the east that would have been eaten up by this fire. So there was adventure there. This is now at our Louisiana Observatory. Can you all see these rods? They don't show up too well. These are rods marking the path of gunfire. And so it was hunting season in Louisiana, and we got shot at. And then this cartoon actually showed up in the local newspaper that said it's hunting season, time to turn on the self-defense lasers. And so we've seen a lot of really exciting, fun things there. And here's me working at the observatory in the control room. and with my own graduate students. So this is another thing that happens. You grow older and then you get students instead of being a student. But I'll end with this. So I told you that, you know, these are very exciting things. We've discovered black holes and neutron stars. That's not what we're going to remember 100 years from now. So look at this. We believe Galileo was the first person to turn a telescope into the sky 400 years ago. Until then, we humans used to look at the sky with our naked eyes and wonder and marvel at what's out there. We used to sit there laboriously night after night marking the paths of different stars and planets, but we didn't have any details. We just saw little dots of light. 300 years later, we had learned from going from this little 1.5-inch telescope to a 100-inch telescope. Another 100 years later, we had put a 100-inch telescope into space. Today, we're building 25-meter-long telescopes. And in the meantime, in these intervening years, we've also turned on telescopes of every possible color of light, from infrared to X-rays to radio waves to gamma rays. And that's taken 400 years. It didn't happen overnight. No one remembers what Galileo saw from his little telescope. He actually saw craters on the moon, which we now can see with the telescope that we buy at the toy store. What was important about Galileo was the paradigm change, that humans do not have to look into the sky just with their naked eyes anymore. You can use powerful instruments. And I think that's what we've done. We've said, you do not have to look at just light, you can look at gravity. So I'll leave you with this thought to ponder.